welcome. In this video segment, I want to expand on some previous videos where we were discussing intermolecular forces. Now, one I think, and I didn't used to teach this a lot, but man, I've grown fond of this. And that is the use of Coulomb's law whenever I'm talking about attractive forces. I think at a kind of level 1 or level 2 understanding of structure determining function, which is a key theme throughout chemistry, I think it has a very powerful way of explaining attractions and repulsions and how substances are going to function and what their properties are. And in this video, I'm going to be applying it to intermolecular forces. Now remember, hopefully if you saw my other video, those are forces of attraction between neighboring molecules. Just a shout out to Jane Smith. She got me saying that neighboring molecule, neighboring molecule, neighboring molecule. And I think it has helped students understand the distinction between bonds between atoms and neighboring molecules, bonds between separate and discrete covalently bonded molecules. Okay, now in Coulomb's law, what we're looking at is potential energy, and as you increase the charge magnitude, in our case we're talking about partial positives and partial negatives, or even temporary positives and temporary negatives. Okay, what you're going to do if you increase that magnitude or you decrease the distance between the charges, you increase attraction, assuming opposite charges. So what that means is we're talking about a more negative or a lower potential energy. So if you graph potential energy versus distance, negative is going to be attractive forces, positive would be repulsive forces. So if we have a lower or more negative potential energy, we're talking about a greater attraction. And the greater the attraction, the more energy it takes to break the attraction. So we can talk about that with permanent dipole molecules, permanent dipole intermolecular forces. We can talk about it with London dispersion intermolecular forces. We can talk about it with hydrogen bonding. And I think it can be a very, very important concept to understand. Now, given the same size, this is really important. Given the same size, the same, therefore, electron density or similar electron density, we can say that the attraction for hydrogen bonding is greater than the attraction for dipole-dipole, which is greater than the attraction for London dispersion. That's given the same size. All right, so you should know that. And when I'm assigning a molecule, a covalently bonded molecule, I'll automatically start, well, if it's a molecular covalent, it has hydrogen bonding. If it's polar, it has the stronger dipole-dipole. If it has an H bonded to an N, an O, or an F directly, not a C, not a C. CH bonds do not have hydrogen bonding. I would add an HB larger. And now that hydrogen bonding, depending on how the question would be asked, that hydrogen bonding would be my dominant intermolecular force. All right, now, one thing you always want to make sure you do is define your distance term. If it's an ionic substance, you say you're looking at the force of attraction between cation and anion. If it is a dipole-dipole, you want to make sure you're talking and referencing very carefully. Got to clear this real quick. You're referencing the attraction between the partial positive on one molecule attracted to the partial negative on the neighboring molecule. So always define that distance term. We can use Coulomb's law with atoms, and we can talk about between the electron and the positive charge on the nucleus. So it's very important to define your distance term when you're applying Coulomb's law. All right, now here's where things get interesting, and here's where you're going to see a lot of the questions focus, and that's on London dispersion. London dispersion can get very strong. And honestly, the hydrogen bonding on a small molecule can end up being weaker than the London dispersion on a large molecule. So there's like a tipping point where that happens. And I'm telling you, in terms of certainly AP and IB, most, I think, general chemistry, but listen very carefully to your professor about that, the tipping point will be indicated by data. So you will have a very large melting point for London dispersion compared to a smaller melting point for hydrogen bonding. And that will be your clue that you're like, oh man, I thought hydrogen bonding was stronger, but the melting point is telling me that London dispersion is larger, or the boiling point is telling me that London dispersion is larger. Oh my gosh, mind blown. Well, no, let's not have that be a mind blown. Let's understand it. And I am so grateful for one of my students. They so often bring me great mnemonic devices, and I so wish I remembered her name. But she came up with the phrase London in September. So whenever you see that tipping point, whenever that tipping point is provided by data, here's what you want to reference. That London dispersion forces, as you increase the size of the molecule, you increase the electron density. There's just on a time averaged basis more electrons in probability in a given area. You're going to increase the polarizability. I'm going to give an analogy for that in just a minute. The polarizability is the ability to shift electron density. Okay, to move those electrons from one side of the molecule to the other side of the molecule. And when that happens, I have an increase in my temporary dipole. And I'll tell you, on the AP test, every year, I bet my kids Butterfinger bars that this will be an answer to a question on either the multiple choice or the free response. And I win every year. And then I beg them not to bring me Butterfinger bars because I'd get like really fat. And then I'd have a large polarizability and an increased dipole because you could push that fat around. Think Jabba the Hutt. Okay, now let me give you a little bit more pleasant example of polarizability. So what I like to think about is at a baseball game, you have a wave. Okay, and what happens is everybody's sitting down and suddenly with seemingly no reason, a person stands. And that person standing induces or causes another person to stand. And then that induces the next, and that induces the next. And pretty soon you have this wave of people. Now, those people don't stay standing. Eventually they sit down. And you end up with the wave at the ballpark. So they stand and then they sit. It was a temporary event, okay, much like London dispersion. Now, as you increase the molecule size, or you can think of it as a taller person. So maybe this is a bunch of little kids out in the bleacher, but if you have a whole bunch of tall adults, when they stand, the wave is going to be taller. Still temporary, but taller. So this would be a larger partial positive to partial negative than the kiddos in the bleachers would have a smaller partial negative and a smaller partial positive. So I think that has a little bit of help on that. And then there's one more thing you want to look at is distance. In addition to size, contact area increases. So the closer the molecules can kind of snuggle together, the stronger the London dispersion forces. And so that, I think, is another important consideration. Although size is the one that comes up most often, that contact area is really, really important. So I kind of think of fats that can kind of snuggle up against each other. That would represent a fatty acid chain, maybe, like what you would see in biology in a cell wall. So if those chains can kind of snuggle up together, then they have strong contact. But if for some reason there's a kink in one of those, then they're not as close, so they have less contact. So this would be a weaker London dispersion. Okay. Well, I know that was a long video, but it was an important one. Rewind that if you need to hear it again, and thanks so much for your attention.